Hi, this is Chris. This video continues the discussion of how to build a circuit to perform floating point division. The study question from last time was, why does using ASIG in place of computing the remaining bits of Y bar result in correct rounding? After NSIG plus 3 iterations computing the significand of the quotient, we have two cases. The first digit of the quotient is 0, and the quotient needs to be renormalized. Or, the first digit of the quotient is 1, and the quotient doesn't need to be renormalized. Starting with the first case, to be able to round the significand, we need to have the significand itself, the most significant bit of Y bar, and we need to know if the remaining bits of Y bar are 0 or non-zero. After NSIG plus 3 iterations of computing the significand, because the first digit of the quotient is 0, we only have NSIG plus 2 significant digits. The first NSIG plus 1 bits are the significand, which needs to be rounded. The remaining bit is the most significant bit of Y bar. We don't yet know if the remaining bits of Y bar are 0 or non-zero. I need to show that the remaining bits of Y bar are 0 if and only if ASIG is also 0. Assume that ASIG is 0. Remember that after NSIG plus 3 iterations that the value of ASIG is really ASIG sub NSIG plus 3. In the next iteration, we need to compute ASIG sub NSIG plus 3 times 2 minus BSIG. We know that BSIG is non-zero, and we have assumed ASIG sub NSIG plus 3 is 0. So ASIG sub NSIG plus 3 times 2 is 0, and ASIG sub NSIG plus 3 times 2 minus BSIG is less than 0. Therefore, ASIG sub NSIG plus 4 and the next bit in Y bar will also be 0. By induction, all subsequent bits of Y bar will also be 0. Now assume ASIG sub NSIG plus 3 is non-zero. Because of how ASIG sub NSIG plus 3 was computed, we know that it's less than BSIG. Because ASIG sub NSIG plus 3 is non-zero, there exists some value n such that ASIG sub NSIG plus 3 times 2 to the nth power is greater than or equal to BSIG. For that value of n, ASIG sub NSIG plus 3 plus n, the corresponding digit in the quotient will be 1. So for the case that the quotient needs to be renormalized, I've just shown that the remaining bits of Y bar are 0 if and only if ASIG is also 0. Now we consider the case that the quotient significand doesn't need to be renormalized. We've computed NSIG plus 3 bits of the quotient. Again, the first NSIG plus 1 bits are the significand to be rounded. The next bit is the most significant bit of Y bar. The last bit is the first of the remaining bits of Y bar. We now have two subcases. The second most significant bit of Y bar is 1, or the second most significant bit of Y bar is 0. In the first case, the value of ASIG is irrelevant because we already know that the remaining bits of Y bar are non-zero. So whether ASIG is 0 or non-zero, appending ASIG to QSIG before rounding the significand doesn't change the results of rounding. For the second subcase, that is, if the second most significant bit of Y bar is 0, then I need to show that the subsequent bits of Y bar are 0 if and only if ASIG is also 0. Here I get to play at being the mathematician I was trained to be.
We've reduced the problem to a previously solved problem.
That is, from here on out, the proof is the same proof as I showed for the first case where the quotient needs to be renormalized.
Quod erat demonstratum.
Ah, come on. You knew all along I had it in me to be a pompous blowhard. So far, all of the circuits in this series have been somewhat unrealistic. All of the computation circuits presented thus far have been pure combinatorial logic. Real floating point units, and for that matter, real CPUs, are really state machines. Time for a little diversion into CPUs. Since the 1980s, much of the computer industry has shifted to RISC architectures. Each machine instruction is broken into phases so that its execution can be pipelined. For example, An instruction might be broken into the following phases. Fetch the next instruction from memory. Decode which registers are used by the instruction. Execute the instruction, and write the result to memory or a register. This example has a 4-stage pipeline. The pipeline would be processing 4 separate instructions simultaneously, each in a different phase. Hopefully, you're already familiar with the general concepts of pipeline processors. If not, there should be a link on your screen now explaining the mechanics in more detail. This link is also available in the comment section of this video. In my hypothetical floating point processor, which uses 4 stages, we can still probably perform the instruction fetch, instruction decode, and writing the results in 1 clock cycle each, as we might do for integer instructions. Where floating point computations complicate things is in the execute stage. The execution of an instruction might take several clock cycles. Worse than that, some floating point instructions might need 1 or 2 cycles for the execute stage, where other instructions might need 10 or more cycles to complete. So far, none of the arithmetic circuits which I've presented in this series has used a clock. A clock hasn't been needed because all of the circuits so far are pure combinatorial logic. It's true that the FPGA test harnesses for multiplication, addition, and subtraction have a clock which drives the harness, but I've always picked a clock speed slow enough that the arithmetic operation finishes in 1 clock cycle. The implementation of today's version of the division circuit breaks with this precedent. This version of the division circuit computes the quotient using a state machine which is driven by a clock. More than that, the state machine, depending on the input values, will complete in a variable number of clock cycles. For this reason, the state machine generates a signal to inform the rest of the system that the operation has completed. The state machine has another difference. My goal in designing an FPU is to figure out how to make it as fast as possible. You might remember from my earlier series on optimizing the performance of the circuit which multiplies the 2 significands that each time I improved the performance of the circuit, I did so at the cost of more gates. There are situations where speed isn't the most important factor. Conservation of chip real estate might be more important in some applications. The previous video used NSIG plus 3 subtraction circuits to compute the quotient significand, and that was before the addition-subtraction logic used by the rounding module. Today's circuit, because it's a state machine and reuses much of the arithmetic logic, only uses 2 subtraction units to calculate the quotient significand before passing control to the rounding module. Before implementing the division logic, let me point out something else. We need to be able to process 6 different categories of floating point data: signaling nands, quiet nands, infinities, zeros, normal numbers, and subnormal numbers. Anytime the circuit needs to divide using nands, infinities, or zeros, we don't use long division to compute the significand. That should mean that when we process these exceptional cases, that the circuit can finish more quickly. The sequence of events will be: present the inputs, dividend, divisor, and rounding attribute to the state machine. Send a start signal so the state machine will begin computing the result. The state machine will examine the operands to determine how many cycles are needed to complete the computation. The state machine will loop until the operation is complete. In the last cycle needed to compute the result, the state machine will signal the rest of the system that the results are completed. Here is the entry to the module. In the division circuit from the last video, the input values were the dividend, divisor, and rounding mode. Today's circuit adds 2 additional inputs, the system clock and a start signal which causes the state machine to begin execution. The outputs from the previous video were the quotient, a bit vector reporting whether the result was a nan, an infinity, a zero, a normal number, or a subnormal number, and an exception vector to report any errors that were generated by the computation. Today's circuit adds an output signal to indicate that the computation is done. The code waits at an always block for the clock and the start signal. Every time the clock goes high, the always block is repeated, but no work begins until the always block sees the start signal pulsed into the module. Outside of the always block are two instantiations of the FP class module to decode the dividend and divisor. This isn't new except for this subtle point. Because the dividend and divisor are presented to the divide circuit before the start signal is asserted, the FP class modules will already have had time to have decoded the data types of the dividend and the divisor. This means that when the start signal is asserted, the output of the FP class instantiations will already be available, so the circuit won't have any additional delay waiting for the output of the FP class modules. The circuit immediately uses the dividend and divisor flag values in a case statement to separate the exceptional cases from the case when we actually have to perform long division. For the exceptional cases, the case statement computes the result and sets a counter which keeps track of how many additional cycles are needed. For the exceptional cases, only one additional cycle is needed to complete the computation. In the case that we need to perform long division to compute the quotient significand, the case statement computes the first bit of the quotient and sets the count of the remaining cycles to n sig plus 4. As long as the remaining cycle count is greater than 0, the state machine is driven along by the system clock. For the next n sig plus 2 cycles, the state machine computes the next bit of the quotient significand. In the following cycle, after the final unrounded bit of the quotient significand is computed, the state machine optionally renormalizes the quotient significand and decrements the quotient's exponent. Between the end of this cycle and the final cycle, the data is passed to the rounding module outside of the always block. The rounded significand and exponent values are available for the last cycle to construct the return result. The logic block for the last cycle is shared with the exceptional cases. However, for exceptional cases, the return result was computed in the first cycle of the state machine, so the circuit uses a flag to prevent overwriting the previously computed result. That is, the logic for the final cycle only constructs a return value in the case that the circuit needed to perform long division to compute the quotient significand. Outside of the main always block, there is a second always block. Its job is to monitor the remaining cycle count each clock cycle. When the cycle counter goes to 0, the second always block asserts the done signal for 1 clock cycle. On your screen is the signal trace for a simulation of what happens when the circuit is asked to divide 0 by 0. You can see the dividend, divisor, and rounding mode are presented to the division module, and then the start signal is asserted for 1 cycle. In the trace, take note of the Q value and Q flags. You can see that they are both available at the end of the first clock cycle. In the second clock cycle, the circuit asserts the done signal and the state machine returns to an inactive state. This trace is for the case in which the division circuit needs to perform long division. Again, the dividend, divisor, and rounding mode inputs are presented, followed by a pulse of the start signal. Each cycle, the module exports Q to the outside world for diagnostic and didactic purposes. That is, as each new bit of the quotient significand is computed, we can watch its progress. In the last cycle, the circuit finally constructs the final return value, and again, like the exceptional cases, asserts the done signal for 1 clock cycle. One other thing to note about the done signal. It's asserted and deasserted on the falling edge of the clock. That way the signal meets any necessary setup and hold times to be successfully monitored on the rising edge of the system clock by other components in the system. Now that you've seen the simulations, it's time to show the circuit in operation. I created a test harness to exercise the division state machine on my FPGA development board. The clock which drives the state machine ticks once per second so that we can examine the progress as the long division of the quotient is performed. The FPGA test harness has 3 registers, one for each of the dividend, the divisor, and the rounding mode. The dip switches on the board, in conjunction with the left, right, and center push buttons, can be used to change the register values to any set of values desired. When the FPGA is first programmed, the default value of the dividend is 355. The default value for the divisor is 113. The default rounding mode is round ties to 0. Once the FPGA is programmed, you'll see the steady pulse of LED 15. This is the 1 Hz system clock which drives the division state machine. When you press the upper push button, you'll see LED 12 light. This LED will stay lit as long as the button is depressed. When the upper push button is pressed and held, you'll see LED 13 pulse on and then off in a single cycle of the system clock. This LED corresponds to the start signal. As soon as the start signal LED comes on, it's no longer necessary to press the upper push button. You'll see the quotient being computed bit by bit on the 7-segment display. Since we're dealing with binary 16 values, the quotient significand will be computed to 13 bits. Then, if the quotient significand is not normalized, as for this case, you'll see the significand shifted one more place to the left, and then the final cycle will display the computed result. Restart the divider by pressing and holding the upper push button a second time. Now, rather than watching the computation of the quotient significand, pay attention to LED 14. You'll see that at the end of the computation, this LED comes on and then goes out again at the end of the cycle. This LED is driven by the done signal. Now, let's perform an exceptional case. Let's divide by 0. To do this, place all of the switches into the off position. Press the right push button. You'll see LED 7 come on while the button is pressed. While looking at LED 11, release and re-push the right push button. You should be able to see LED 11 quickly flash on and then off. It happens really fast, so you may miss it. This is the signal which clocks the value set on the switches into the divisor register. We're now ready to run the division state machine again. Press and hold the upper push button until you see the start signal flash on LED 13. This time, the state machine completes in only 2 clock cycles, and positive infinity, that is hexadecimal 7C00, is shown on the 7-segment display. If you wish to change the dividend register, set the dip switches to the desired value, and then press the left push button. While the left push button is pressed, you'll see LED 9 lit. Like pushing the right push button, you'll see LED 11 flash on, then off. To change the rounding mode, set dip switches 0 through 4 with the desired value. Remember, one and only one of these switches should be on when selecting the rounding mode, and then press and release the center push button. When the center push button is pressed, you'll see LED 8 come on and stay on as long as the button is pressed. As when setting the dividend and divisor registers, when the center push button is pressed, you'll see LED 11 quickly flash on, then off, as the rounding mode is latched into its respective register. Finally, if you want to restore the original dividend, divisor, and rounding mode values, press and release the down push button. The corresponding LEDs are numbers 10 and 11. As long as the down push button is pressed, LED 10 will be lit and LED 11 flashes on, then off, as the reset signal is sent to the dividend, divisor, and rounding mode registers. You can verify that the register values have been restored by pressing the upper push button until LED 13, the start signal, lights. If the board was successfully reset, the final value shown in the 7-segment display will be 4248 hexadecimal. When the division computation is completed, there may be one or more exceptions which have occurred. Exceptions are displayed on LEDs 0 through 4. LED 0 corresponds to the invalid exception. LED 1 indicates divide by 0. LED 2 represents overflow. LED 3 is for underflow. And finally, LED 4 indicates an inexact result. If you press the down push button and reset the registers to their default values and rerun the division using the up push button, at the end of the computation, LED 4 will be indicating an inexact result was computed. Take some time to play with the circuit, putting in various test values, signaling nands, quiet nands, infinities, zeros, etc. Also be sure to test dividing normal and subnormal numbers. Feel free to download the code and experiment with it. One possible change to the code would be to replace the done signal with a wait signal. A wait signal would be asserted in response to the start signal being asserted, and the wait signal would be deasserted when the clock count becomes 0. This might allow the exceptional cases to complete in a single clock cycle. The current system clock is running at 1 Hz. This is artificially slow so that we humans can observe as each bit of the quotient significand is computed. You might experiment with how fast the system clock can be made to run and still have the circuit produce correct results. Along those lines, you might test whether computing each bit of this quotient is slower than the rounding of the significand. If rounding limits how fast the clock can run, then it might be possible to compute 2 bits of quotient per clock cycle in the first part of the state machine and still achieve better performance. I'm sure there are other experiments which can be run as well. Thinking about the problem from different angles will help you gain mastery of the subject. Also, if you port the code to another FPGA board, please let me know so I can add your code to the GitHub repository for the benefit of others. The state machine saves gate resources in 2 ways. The first of these I spoke about earlier. This state machine only uses 2 subtraction units to compute the unrounded significand of the quotient. This is a savings of 11 subtraction units for the binary 16 data type. For the larger IEEE floating point formats, it's a savings of 24, 53, and 113 subtraction units for the binary 32, binary 64, and binary 128 floating point formats respectively. The second way this circuit saves gates is related to reducing the number of subtraction units. As the sign of the operands increases, we don't just require more subtraction units, we require larger subtraction units. 113 subtraction units computing 115-bit quotients requires a lot of chip real estate. The downside is that this circuit requires, worst case, nsig plus 5 cycles to compute the quotient. For the binary 128 floating point format, this means it will take 117 cycles to get the final result. Perhaps you, like I, have heard that as much as possible when performing floating point arithmetic that division should be avoided. The topic of avoiding floating point division will be taken up in the next video. Before heading off, take note of the links which I placed in the comments for this video. One of the links is a brief video about instruction pipelining if you need an introduction. A second link is to the class notes for implementing a MIPS processor. I haven't studied the notes, but do want to point out something I think is important. Page 4 of the class notes cites an instruction latency of 0 cycles for integer instructions, 3 cycles of latency for floating point addition, 6 cycles for floating point multiplication, and 24 cycles for division. Even among floating point operations, division is very, very slow. As usual, the comment section gives the location of the GitHub repository for the code described in this video. Please share this video with friends and colleagues who might have an interest in this series. Questions and comments are welcome in the comment section. If you found this video useful, please click like below. While you're at it, subscribe to the channel, then click the bell to be notified when new videos are available. Thanks.